Understand the principle of electricity. Everything that exists in the universe is made up of particles like atoms. An atom consists mainly of a nucleus which contains protons and neutrons. Around the nucleus gravitate particles called electrons. They are a bit like satellites that revolve around the Earth. When electrons move from one atom to another, we say that there is an electron movement. This movement is the electric current or electricity. How can we cause the movement of electrons to produce electricity? You must first have a conductor in which the electrons can move easily, for example a copper wire. And how do we get electrons to move in a conductor? We use the magnetic field of a magnet. If we bring two magnets together, two things can happen: either they repel each other or they attract each other. Let's imagine that we sprinkle iron filings on a magnet. We see lines of force appear, which shows how the magnetic field is distributed around the magnet, a bit like the Earth. The magnet has a north pole and a south pole. If we bring two similar poles together, for example two north poles, the magnets repel each other. If we bring together a north pole and a south pole, the magnets attract each other. The source of this force is the magnetic field. When you move a magnet in front of a conductive material, the magnetic field has an immediate impact on the electrons. Indeed, the electrons move in one direction or the other. Depending on the pole that passes in front of them, the magnetic field therefore causes a back and forth movement. A round trip of electrons in the conductor, the variation of the magnetic field caused by the rotating moments plays an important role in the production of electricity. If the shoulder of the magnet does not move, the magnetic field does not vary. There is therefore no induction of electric current in the conductor. On the contrary, if the conductor is constantly subjected to a variable magnetic field, an electric current is created. This is how electricity is produced. There are two types of current: alternating current and direct current. When the electrons always move in the same direction, the current is direct. When the electrons move back and forth in the conductor, the current is alternating. But how is electricity produced every day in a large electricity grid like ours? To fully understand the phenomenon, we must go to the source in the hydroelectric power stations, where the turbine alternator groups are located. In the previous example, we saw how the two poles of a moving magnet produce an alternating electric current in a conductor. If you want to generate a lot of electricity using powerful alternators, you have to do the same thing, but on a completely different scale. An alternator is made up of two main parts, a rotor and a stator. The outer wall of the rotor is made up of several magnets with the north and south poles arranged alternately. These magnets rotate inside the stator and the stationary part of the alternator, and is formed of a copper bar winding which are conductors to induce an electric current. The magnetic field must vary. The magnets must therefore be mobile. The rotor rotates while the stator, which contains the copper coils, remains stationary. Let's imagine a single magnet and a single conductor. The electromagnet rotates, passes the conductor, and induces the electric current. As the conductor is subject to rotating north and south poles, an alternating current is generated in this example when the rotor turns once. The stator sees two poles, a gold and a south. The alternating current therefore made a round trip, either 1 cycle or 1 hertz. In general, electrical networks have 50 or 60 hertz. At 60 hertz, that's 60 cycles per second. It's a lot of 1 cycle. It's the passage of 2 poles in front of the conductor, so 60 cycles per second. That's 120 poles per second. If there was a single magnet, it would have to rotate incredibly fast to reach 120 poles per second and 120 poles per second. This is 60 Hz, the frequency of our electric model. If the alternators all had different frequencies, it would not be possible to connect them together in an electrical network. This is why the continents almost always have the same frequencies, 50 and 60 Hz. But what determines the rotor speed in a hydroelectric power plant? These are the hydraulic turbines that turn the rotor. For the water to transfer its energy to the turbine, it must fall from a certain height. This is called the height of fall. It is this which determines the rotation speed of the turbine. The higher the water falls, the faster the turbine turns, so that the frequency of the electricity is 60 Hz. Each of the copper bars of the stator must see 60 north poles and 60 south poles pass by second, therefore 120 poles in total each second. Remember that 120 poles per second is 60 Hz. We know that electricity is an invisible phenomenon. We cannot see it, but we can measure it to evaluate, for example, the consumption of each house. Let's take a look at the main units of measurement used. Electrical power is expressed in watts and depends on two factors, voltage and current intensity. To fully understand the concept of electrical power, let's make an analogy with the garden hose. In the hose, the water pressure is the force at which the water is projected. The more pressure, the more force, the further the water jet goes. In an electric wire, it's the same thing, the voltage pushes the electrons. The higher the voltage, the stronger the electrons are pushed. Where it expresses the voltage in volts. In our example, the water flow is, in a way, the quantity of water drops that come out of the hose. The higher the flow rate, the greater the amount of water that comes out. The drops are the electrons in our electric wire. It represents the intensity of the current. The higher the intensity of the current in a wire, the more electrons flow through it. The intensity of the current is expressed in amperes. The power of the water jet is the combination of its pressure and its flow rate. Thanks to these two factors, pressure and flow, water can move an object. It's the same thing for electricity, it is the combination of the two factors, namely the voltage in volts and the intensity of the current in amps, which determines the power of electricity in watts. Let's put this power in a real context. When a bulb is lit, it consumes energy which is measured in water. If we leave a bulb with a power of 10 watts on for 100 hours, it consumes 1000 watt-hours. 1000 watt-hours is a kilowatt-hour. It is a kilowatt-hour which is produced electricity. In recent years, innovations have paved the way for significant new advances. The energy stream system simplifies electricity production for private use. This technology exploits the advanced capabilities of alternators to excite electrons, and maximizes the production of electrical energy. In addition, the autonomy offered by the energy stream system represents a significant turning point in the field of domestic energy outside traditional networks. It opens the way to a more efficient and accessible use of electrical energy. The concept of energy stream technology offers the possibility for everyone to become a producer and consumer of electricity in an autonomous, sustainable manner with minimal maintenance. Smart Life Streams and its partners aim to make energy accessible to everyone through the potential of its energy stream technology. In a rapidly changing world, energy autonomy is the key to prosperity for us all.